예, 안녕하세요. 그 두 번째 튜토리얼 좀 시작하도록 하겠습니다. 예, 오늘 그 두 번째 발표를 맡아주실 분은 이제 숭실대학교 권민혜 교수님이시고요. 제가 간단하게 좀 양력과 그 리서치 인터레스트 소개를 드린 다음에 이제 바로 이제 튜토리얼로 넘어가도록 하겠습니다. 권 교수님은 이제 이화여대에서 이제 학위를 하시고, 그 다음에 베일러 컬리지 오브 메디슨, 그 다음에 이제 라이스 유니버시티 등에서 이제 포스트학 펠로우로 이제 근무를 또 하셨습니다. 그 다음에 작년부터는 숭실대학교에 이제 부임을 하셔서 다양한 재미있는 주제로 연구를 하시고 계십니다. 그 뭐 연구 이제 토픽으로는 이제 여러분들 뭐 다 많이 관심이 있으실 만한 reinforcement learning, multi agent 뭐 learning 이런 부분을 많이 연구를 하셨는데요. 전체적으로 모바일 네트워크, 뭐 컴퓨테이셔널 뉴로사이언스, 뭐 브레인 사이언스, 뭐 인공지능 기반의 여러 시스템 이런 것들을 다양하게 연구를 하고 계십니다. 오늘 톡 해주실 주제는 뭐 제목이 저도 좀 궁금하긴 한데요. 내용이 어떨지. Modeling Minds a Reinforcement Learning Perspective라는 주제로 오늘 발표를 해주실 예정입니다. 오늘 이제 튜토리얼 해주실 권 교수님을 박수로 한번 맞춰주시면 감사하겠습니다.
네, 안녕하세요. 숭실대학교 권민혜입니다. 제가 오늘 이 튜토리얼을 영어로 진행해달라고 리퀘스트를 받아서 그 중간중간 내용은 다 영어로 진행을 할 예정이고요. 혹시라도 이제 질문이 있으시면 언제든지 스톱해 주시고 질문은 한국말로 하셔도 저 다 알아듣습니다. 다 알아들으니까 네, 편하신 대로 해주시면 될 것 같습니다. 그러면 이제 튜토리얼 진행하겠습니다. Good afternoon, everyone. I'm so glad to have this a great opportunity to have my presentation. So today I'm going to talk about the modeling minds. I'm going to give you a perspective of reinforcement learning. So my name is Minhae Kwon. I'm a assistant professor at the Sungshin University. Sorry about it. There is some technical problem right now. Yeah, okay. So here's the outline. I'm gonna draw 3 questions during this tutorial session. So the first question is, how do we make decisions? As soon as you heard about this question, you might be really curious, like, do we know even how do I make a decisions? So I'm gonna introduce the deep reinforcement learning approach to explain this question. And the second one is, then how can we model the mind of others? Yeah. So I'm going to introduce like inverse rational control that I published in Neuroscience last year, and then try to explain how do we model the others. And the last question will be, where can we use this approach? So I will introduce the mixed autonomy traffic and cooperative network formation of the mobile networks. So let's start the first part. So imagine that you are behind the wheel. So every moment you're driving, you make a decision, right? So the first thing you do is you make observation. You look at the road in front of you and you look at the passing trees. And based on that observation, what you do is you make a belief. You estimate the speed of my current vehicle and my location. So make sure I'm on the right in the middle of the lane, and also directions. So based on that belief, I make a action. So I can rotate car steering wheel if I'm not in the right location, and sometimes I press the brake pedals or acceleration pedal. So my action changes the world, and then I get a new observation, and I make a new belief, and I make a new action, and also change the world and keep going. So like this process is what we are doing every day, every moment, and right in this moment. So what I'm gonna do is, I try to explain this decision-making process based on reinforcement learning. So you've probably heard about reinforcement learning a lot of times. So let me just briefly give you the introduction. So there is a 2-part in reinforcement learning. The first part is the agent, and the second part is the environment. So in terms of the agent, from the perspective of the agent, at each step, we make observation. And update the belief, and execute an action, and receive a scalar reward, which is gonna be like from the environment. And if we look at the perspective of the environment, it's exactly the same process, but the environment receive an action, update its state, and emit a scalar reward. That's a process and interaction between agent and the environment. And we can model it based on belief Markov decision process. So this is the general structure of the belief Markov decision process. We also call that in belief MDP. So yeah, it's exactly the same repetition that I would explain. So first of all, there is a state. That's a true world state. And I'm gonna use it as a representation of the world. And based on the state, I, as an agent, make observation. That's gonna be O in here. And based on all the observation, I make my belief. So the technical definition for the belief is agent's guess about the state. So mathematically, it can be a probability distribution over the state space. I'm going to touch that part in the next slide, so don't worry about it. And based on the belief, I make an action. And the action changes the world, and we get a new state. And from the state, I make an observation. From the observation, make a belief. And this sequence is repeated. So let me explain about the belief Markov chain, belief Markov decision process a little bit more. So I gave a very simple example. So like a lot of people get confused about what is the state and what is the belief. So let's say I'm driving again, and the true world state is the yellow color, the traffic light. And what I observe right now is a big truck in front of me, so I cannot see. I'm so small and like, yeah, I never gonna be able to see the traffic light. But I have another observation. I can see that vehicles are getting slower. Yeah, I can see that. Then my belief will be, I can draw that distribution, then maybe the probability to have a yellow state is the highest. And probably, yeah, it already got the red. So red probability maybe the second best. And I don't think the green is, yeah, like possible, but there is a still possibility. So that's gonna be the belief. Belief is again, the agent guess about the state. So we also sometimes talk about it about like a subject posterior distribution, because that's your belief, not a true knowledge. So yeah, the belief MDP is like this, but it's kind of complicated. So let's just simplify it. So a lot of people mention about the Pomdp. It is a little simpler version of the belief. I would say belief is more realistic, but yeah, a lot of cases it's hard to calculate the belief itself as a distribution. So let's talk about Pomdp in this tutorial. So like, what is the difference between Pomdp and belief is you make a decision based on observation. Forget about the belief. Forget about the probability. You have a state, you have observation. Based on that observation, I make an action. And that action changes the world, and that update the state. And I also make observation. And based on the observation, I make an action. That's a Pomdp. But a lot of cases, even the observation itself has some challenges. For example, like the example that I show, my observation is not perfect. The big truck in front of me, I cannot see the state. So it can be a partial information, or sometimes like, let's say like the view is so blurred, so I cannot see exactly what is going on in front of me. So in the case, a lot of noise is on the top of the state. So yeah, that's why we also call that partially observable. We are not able to get a perfect information. Instead, we get a partial observation, sometimes partial noise observation. So to mathematically talk about the Pomdp, we need 7 tuples like that. So the first one is the state. It can be continuous, it can be discrete, but most of the real world scenario is continuous, definitely. And it can be just a single dimension, but I don't see that really many happens. Most of cases, like high dimensional space. From that high dimensional space, I make a observation. So that's a O, the second one. And from the observation, I make action. The action I notate it as AT. And I also get a scalar reared from the world. So I mark that as RT. And there is a state transition probability, P of ST given as NA. So that's how the true world is changing over time. Also, there is observation probability. So the probability of O given ST is the how do you make observation and how noisy your observation is, how partial your observation is given the state. And there is a discount factor. I'm going to talk about it shortly. Yeah. So yeah, like a Pomdp can be defined based on as such as 7 tuples, and to make a Pomdp problem, you make sure that you have a 7 tuples. And like basic underlying assumption in this scenario is Markov property, so which is also called the memoryless property. So basic assumption in here is a future state depends only upon the present state. Does not depend upon the past. I also sometimes talk about this assumption to my student, like, don't ask me my history. Tomorrow's my status will be only based on today's my state and action. So I'm not going to ask your history. So that's a basic assumption underlying in Pomdp. I know that's kind of a big assumption, but like that makes everything like clear and then easy. So, and a lot of case these days, like people try to tackle that assumption based on LSTM or any other different kind of the neural network. But yeah, that's in mathematically, that's your assumption in Markov decision process. Yeah, so like this Markov property can be explained with the equation like this. So probability of the ST given all the history of the state and all the state of the history of the action, it equal to the same as probability of ST given right before time moment of the S and right before time of the action. So you don't need to hold the history, trajectory of the state or trajectory of action. That makes everything really simple. So yeah, now we have a Pomdp and how to solve it. The exact question that I just asked, how to solve it, can be matched to the question, how to make a good decision. So given the framework of the Pomdp, how can I make a good decision? So this can be explained based on the policy. So what the policy is a solution to Pomdp problem. So for example, in here, a lot of cases, policy can be denoted as the pi. So pi of O equal A. What that means is mapping from the observation to action. So what does it mean is I observed O right now. So which action should I take? I'm asking this question to this policy, and policy returned the perfect action A to me. So that's a policy. If I go back to Belief MDP problem, so it's just the input part of the policy is different. So in case of the Belief MDP, all the decision making is based on the belief. So the belief in Belief MDP, policy is a mapping from the belief to action. So in this case, I'm guessing the word state is like B of S. So which action should I take? So like only the input part is different. And of course, I want to make a good policy. So what is a good policy? It's choosing an action that maximizes the discounted future reward. So yeah, how to find the policy then? So to find a good policy, we first of all evaluate it. To evaluate it, we have a Q value. So what the Q value means is how valuable to choose an action A at observation O. It evaluates the combination of the O and A. So at observation O, I perform A, and I just imagine that my future action selection is going on under the policy pi. In the case I have a discount factor gamma, then what's gonna the value for that given O and A action? So in the combination, we calculate the Q value based on cumulative discounted future reward. So as you can see that the reward is cumulated over time as multiplying the gamma in here, which is always smaller than between 0 to 1. And yeah, you calculate it and then you make an expectation over the future policy, then you get a Q value. There might be somebody ask me, like, why do we discount it? So in some case, we can use the cumulative future reward. In the case, I just summate all the reward every moment. But a lot of cases, like cumulative discounted future reward makes sense. Then why this makes sense? The first of all, the uncertainty due to the environment is stochastic. So the future reward that I have in here is based on my own model. So I mean, like I imagine if I use the action A with this, with this S, then that's gonna give the future state S. And given that future state, I'm gonna probably perform the action A based on my policy, and that's gonna give me the next future state S2. And those like future imagination, your future planning has an uncertainty. So that's why we discount the future reward. The second case, like the worth of the reward can be decay over time. You can think about the hot pizza, or a lot of cases, like to my student, I talk about the like warm soup, like a 곰국 or 찌개. So like as time goes by, it gets saltier and like you don't want to eat it anymore. So yeah, like as time goes by, like the worth of that value is decreasing. And also the lifetime of the agent can be ended at any moment. So you cannot just think about only the future. Somehow you gotta make a goal in a limited time. Also, like the most important thing and the true reason is mathematical trick for convergence. So I get this sentence. Steve Jobs said that if today were the last day of my life, would I want to do what I am about to do today? So that was just what Steve Jobs said. And like I always make a question to my student, like in this case, what's going to be gamma in here? Then you can probably say gamma is 0 in this case. So you don't think about the future, you only care about the immediate reward. So, okay, now you have a Q, the value from the O and A, and how to learn Q over time. So a lot of people already heard about the Q learning. So the most famous one, famous algorithm in reinforcement learning. So the way Q is updated is based on the previous Q plus learning rate multiplied by target value minus the current Q. So a lot of cases we call that the R plus max Q is the target that we want to make the Q value, and then the difference is a TD error, which means a temporary difference error. Yeah, a lot of machine learning lectures talk about it, but I want to make sure that really happens in our brain. So like that's try to mimic how our dopamine neuron learn the new knowledge. So let me briefly talk about, I know like it's a communication conference, but let me briefly talk about the dopamine neuron. So in here, like the mark the area has a dopamine neurons, and what the dopamine neuron does is it causes the temporal difference error. So as you probably all know, that dopamine neuron is the hormone of the pleasure. So when I get happy, I get more dopamine comes out from my brain. So what the TD error does in here, it's a surprise signal. So I expected the cue. That's my expectation. But I actually got this target value. Then if that gap is big, we learn something new, right? And then the dopamine comes out. So that's how we learn in our brain. And also I make this example always. So you knew that you're going to get that award. And you're not that surprised. Then you're not that happy, right? But you never imagined that you're going to get this award. And you suddenly get the notice that, oh my gosh, I'm going to get this award. And you got really, really happy and you're so surprised. So what our dopamine neuron does is encode those TD error. And then we are doing the exact same thing in reinforcement learning. Yeah, so we find the policy, but always as an engineer, we ask it, is it optimal? Is this the best? So to talk about the best optimalness, we need to define the optimal policy first. So what optimal policy is, the policy is optimal if it can maximize Q value. So once the optimal policy is defined, it returns the optimal action A for a given observation O. So when you need to get an optimal action is you need to train the optimal policy. So yeah, the action A, the optimal action comes from the policy given O, and it's actually the function from the argument Q. So the argument that maximizes the Q value and choosing that action. Given this equation, that's like the most important equation, I guess. Then like we have two challenges to find the optimal policy. The first one is how is it to estimate the Q value for high dimensional state or action space? So if that action space or the observation state is really, really high dimensional, how can we find this Q value? That's the first question. And the second challenge will be how to handle the argmax function in continuous action space. So if it is a discrete action space, we can just compare all the Q values of A and then find the argument that maximizes the Q value. But what about the continuous action space? That makes problem harder. So I'm going to introduce actor-critic architecture. So actor-critic architecture can jointly learn Q value and the policy. So there are two neural networks. The first one is answer the first question. How is it to estimate Q value in case of the observation or action space is high dimensional, continuous, whatever that makes harder? We need a critic network, the neural network, the artificial neural network that approximate the Q function. So in this case, I give an input of the O and A as an input to that artificial neural network, and it returns Q. And the way we train this neural network based on the loss function, and a lot of people talk about the gradient descent, and we use the TD error to make that neural network work. So that's my answer for the first challenge. Now we can handle the high dimensional observation or action space. Then what's the next question? How can we handle the argmax function? In the case, that's a problem when we have a continuous action space, right? So in the case, we need an actor network, another neural network, that approximate the policy. So it receives the O and returns the action. And the way it is trained is based on the Q value. We use the Q value as loss function. Then we need a critic network again to train the actor network. And based on the actor network's action, I choose the action that goes into the critic network as an input and return the Q value. The Q value used it in the actor network to train. Yeah, that interaction keep going. And I want to just to briefly mention that that's what is really happening in our brain as well. A lot of people in neuroscience found that in a very central part of the brain, we call the basal ganglia. They do the dopamine stuff over there, and then they do have a critic part which criticize what the current situation is, and also determine the action what's the best action is. So the information exchanging inside of the brain actually is happening, and then we are trying to use that technique in AI. Okay, so far we've covered. So I try to answer the question that how do we make decision? As an animal, what we try to build AI is try to make a copied version of the brain to the machine, right? And then the best role model in here is our brain. So to understand that, how do we make decision? That question is really important. And I try to understand or explain it based on the approach of the deep reinforcement learning. So to have that in mathematical way, I used the Belief MDP, and the simpler version was the Pomdp, partially observable Markov decision process structure. And based on that structure, I tried to find the optimal policy and use the Q value. And to find the Q value or to find the optimal that policy, I introduced the actor critic architecture. Yeah, that's what I covered in the very first question. And it is really important, but that's beyond the scope of this tutorial is exploration. So when we learn that, imagine the little kids, they just try everything. They know what's good, what's bad. They just try everything and get a reward from mom or dad. If mom compliment her, then she does that repeated again. And if she get penalty, scolded, then she never gonna try that one. So we need the exploration part to learn something new. And for the AI, we make sure that AI, the agent, do something new, try something new to learn a new part. So we use the epsilon greedy or Gaussian noise or OU noise. There are many different kind of things, but I'm not going to touch that in here, but that's really important to train the AI. And another thing is there are really, really many different kind of the deep reinforcement learning algorithm. So PPO, data PGTD3, those are the most popular one. That's the first algorithm that my students try. But except that, there are really a lot. And then we get the new algorithm every day. So we can try the very different reinforcement learning algorithm. And you should study that one if you're interested in reinforcement learning. And the last one, neural network training tricks. So unfortunately, training an AI based on reinforcement learning is really hard. Compared to supervised learning or unsupervised learning, it's really hard. It's really really like suffer from the hyperparameter tuning, and a lot of tricks are needed. So I gave just the simple 2 examples, including experience replay and twin networks, but there are really a lot of different kind of training tricks. So you should try check them out. For example, in case of the experience replay, that is used in AlphaGo, as I know. So yeah, a lot of people, especially in Korea, get fascinated about that one. Okay, so that's all for the first part. And that was the general, introduction about the deep reinforcement learning. And now we move to the exciting part. That's the second part. Can we model the mind of others? So I'm gonna introduce you the inverse rational control approach. If you're really interested in this topic, after my tutorial, please check them out. The newspaper that I published last year. And also there is a PNAS paper that we introduced. We firstly introduced the inverse rational control. So yeah. So come back to the same question, but it's a different question actually. Come back to the same scenario, but different question. So do we always make the optimal decision? So like we try to train the AI, and I was explaining that how to train the AI. That's what try to find the optimal policy and how to train the optimal Q value. But as an animal, as a role model of the AI, do we always make the optimal decision? I would say nobody say yes. We all know that we sometimes, but often, make suboptimal decisions. Then what's wrong with us? So try to answer this question. Why do I make a suboptimal decision? The basic assumption we make in here is the agent make decision based on their own internal model. As I explained the belief and the concept in the very beginning, belief itself is a subjective posterior. I just imagine that the traffic light is yellow, but maybe it's a green, but there is so many traffics on the road, so that's why I cannot go. So my belief can be wrong, or can be yes, can be accurate, can be a little bit wrong. Yeah. So all our assumption in here is all the agents make decision based on their internal model, and no guarantee that the agent internal model is correct. So maybe the agent might make the optimal decision under the wrong internal model. That's why that agent make a suboptimal decision. So we call that as a rational agent, not an optimal agent. So the rational agent is the agent that chooses an action that maximizes the discounted future reward based on their internal model, and no guarantee that the internal model is the true world. Then our question will be, can we find the internal model by observing the agent's behavior? If I look at the person and try to look at the person's behavior, then I might be able to understand why he make that some noise, why he behave like that. So what I try to do in this section is I try to find the internal model based on their behavior by observing their behavior. So come back to the belief MDP world. We have a state, observation, belief, action, state. So the state is again the true world. So that's a perfect information, that's a representation of the world. And the agent make an observation toward the state, and the observation is not perfect. It is not perfect. It's a partial. It can be noise. Yeah. And based on the observation, I make my own belief. What's the probability toward the true state? And from that belief, I make action. Action changes the world, the new state. But as you can see, we can divide this process into two parts. The top part, that's based on the true world parameter phi. So that's law of the physics. That's how the real world is happening over there. But in the bottom part, that's based on my mind. I do make observations based on my internal model. I might not to really care. Like somebody show me some score, but I don't really care. Yeah, I make my own observation. And based on the observation, I make my own belief. The belief is subjective, posterior. And from the belief, the way I choose my action is based on my mind, right? So those underlying the black part is the based on agent's internal model theta. So we now have two different parameters. The top part, true world parameter phi, and the lower part is the agent internal model theta. And no guarantee that my internal model theta is exactly the same as the true world parameter phi. So yeah, let's find the internal model parameter by catching firefly. So why does she talk about firefly? I was expecting that we might have a lot of young kids in this auditorium. So I was about to explain about what is a firefly, because as a person who grew up in Seoul, I never see the firefly during my life except 2 times. So first of all, firefly is the Pomdp. So yeah, it's really hard to see in big city, but you can see that in a very clean place. So as a when I saw the firefly, the first case I went to the Malaysia, and the second time is I visited my postdoc supervisor's hometown. So I'm going to introduce you the neuroscience experiment, but how that comes from is my postdoc advisor, when he was young, he used to catch a firefly just for fun. And then he built this neuroscience experiment. So now I'm going to introduce neuroscience experiment because I want to find the internal model. And then to find the internal model, we need a brain, real brain, I mean. So we use a monkey, we use a human. So in this case, I give an example. The monkey played a video game. He used the joystick. He wear the VR eyeglasses, and he watched the screen, VR screen. So if we move the joystick, he feel like he are moving inside of the VR world. So yeah, he kind of imagined that he is like walking around inside the VR world as he moved the joystick. And he see the firefly show up and disappear. Oh, what I missed it, firefly always show and disappear. So that's why it's really hard to catch that one, because you see that and it disappear, so you got to remember where it is. And the firefly show up and disappear, and the monkey move the joystick and move inside of the VR world. And as you move the VR world, there is an optic flow on the floor, so that gives you a sense of the movement. So if you move faster, that optic flows drift faster. And if you move slower, it moves slower. If you stop there, it never moves. And if you catch that one, then you get a banana. Yeah, reward. So that's how we reinforce the agent, right? So what is really important to get a banana? Actually, in a real neuroscience experiment, we give them juice. So before having the experiment, we never give them water or juice to the monkey for like 3 hours, 5 hours. So they are really thirsty enough, and then they really do their best. And then if he stopped inside of the reward zone, then he get a juice. So he become really happy. And if he stopped outside of the reward zone, then he cannot get a juice. And we can control the level of the video game as make the reward zone bigger or smaller. That's one like simple manufacture. And this is the photo that we tried. So this is Jack Pico, Professor Jack Pico. He's my postdoc supervisor. He's a professor at Rice University in Texas, and he is wearing actually 3D eyeglasses, and the moving chair is moving, and we have a screen right in front of it, and he uses a joystick. This is a human version, and we also have a monkey version as well. So this is a video that I took when he played around with the machine. So you might see the green circle show up and disappear. So the green circle is a firefly. The monkey thinks like that's a firefly. And then as he moved the joystick, you can see that, let me replay it. As he moves around, you can see that the optic flow, that's a firefly. And optic flow on the floor is drift. And then there's no landmark. You cannot remember where you are located in. What you need to do is you need to calculate how far I have been, how close that firefly with right now. And this is monkey version. So on the left top corner, you can see the monkey's hand. So monkey is like using joystick. And then you can see that monkey version, the video game is way harder than human one. You don't have that many optic flow on the floor, so it's really hard to estimate your velocity and angular velocity. And monkeys are really good at it. So the monkeys are using the joystick, and they try to catch the firefly. And once he believes that he's in the right stop, he press the stop button and then get a juice. Okay, this project is what I suddenly talk about the neuroscience project is it explains the same process that I've explained in a driving scenario. So the monkey or human or Jack make observation, firefly show up and disappear, and you can see the optic flow drift on the floor. So you can get a belief, which is the estimation of your location, your direction, your speed. Based on that, your belief, you make an action. So your action in here is to control the joystick. So which it can be a direction or like force. If you push the joystick harder, then make yourself faster. So those process, internal model and those decision-making process, exactly same as we make in our life when we drive right in this moment. And I try to find the internal model of that monkey or Jack based on this model. Then, of course, we need a computational model. But I think we can take a break in here. Our brain needs time to organize the new information. So maybe 15 minutes? Yeah. 15분만 쉬다가 다음 마저 진행하겠습니다. Okay, let's get started again. So, come back to this slide. We make what I show is the Firefly project. That's a neuroscience project. You try to understand the brain, and the whole experiment is designed to mimic how do we make a decision in everyday life. And that you can see that that's exactly same as the autonomous driving scenario, exactly same as a lot of new decision-making process, what we did. So try to make a computational model and then come back to the slide. So I want to focus on the observable and latent part. So if you can see through the circle, then that's the observable part. From the perspective of the experimentalist. So imagine that the monkey is doing this experiment, and if the monkey played the video game, I can see as an experimentalist, I can see that how the state is changing over time, what action the monkey does, but I cannot see the solid circle in the bottom. So the solid circles is based on monkey's mind. I never understand exactly what monkey really watched, and I never understand what's going on inside of their brain. So those underlying part are the latent variable that I never know, and the top part is the variable that I can see. So a lot of cases, again, the brain is not matched to the true world. So the word parameter phi is not exactly the same as the internal parameter theta. But the agent try to do their best. That means try to find the action that maximize cumulative discounted future reward. So we call that rational. So optimal under the wrong internal model. And we introduced the inverse rational control to find the internal parameter theta. And I give them this example, like this is Kaushik's work, the neuroscientist in my lab, my previous lab. What he does is, what the monkey actually does is always overshoot. So the monkey is supposed to stop this place, but always go further. Always the response is overshoot. So this is the monkey's trajectory, the movement trajectory, and always go further. So you can see that the older red arrow in here, you can see always overshoot. That's what's really happening in our brain. So try to find the true internal model. What I invent is the Bayesian optimal control ensemble. So based on reinforcement learning, of course. So first of all, I parameterize the optimal agent with the task parameter theta. So in here, what I did is from the observation, I make a belief based on extended common filter and make a action based on DDPG algorithm. So those two techniques, I can build the artificial monkey agent theta. And I can change the different task parameter. So I can develop the overshoot monkey or undershoot monkey or different parameter. So each agent I can build based on internal model theta 1. And then I can build multiple agent and then combine those together as a single agent. We call that a multiple personality agent in the case. So that special agent has all the task parameter and then can determine the action based on that input parameter. So to train the optimal agent based on deep reinforcement learning, I use the DDPG algorithm, and as I explained, there is actor and critique. So what actor does, it is a policy network. It returns action given theta and belief. So what is added in here is the theta part. So I give them the internal model and then see that what's going to be action in the case. And then in case of the critique, if I give that internal model, what's going to be the Q value in this case. So that's the way I build the optimal control ensemble. And yeah, that's how I build my artificial agent. And then the goal in here, come back to the question, try to find the internal model theta that explains the observable data the best. So based on maximum likelihood estimation, I try to find the theta that has a highest probability to explain the given data state trajectory and action trajectory. But unfortunately, this state trajectory and action trajectory is based on observation probability, and from the observation to belief, you remember those diagram, right? Then those observation and belief is latent. So in the case, we never know. And then I used a Monte Carlo expectation and maximization by marginalizing it out, and then try to find the theta that can maximize this probability. And on the right side, you can see the surface. So in here, x-axis is the one dimension of the theta, the internal model parameter. Actually, the internal model parameter in my case, it was like 10 dimension. Yeah, 12 dimension, I don't remember exactly, but yeah, that was a pretty high. And I show you like just a 2-dimension, 2D surface, and x-axis is a theta 1 and y-axis is a theta 2. And you can see that the yellow diamond is a true parameter, what I gave them as a true parameter, and then I can find the truth parameter based on my method. So you can see the estimated parameter is very close to the true parameter. And yeah, so this is a successful recovery of the internal model. So x-axis in here is a true value, and the y-axis is estimated value. So if all the dots, the data points are aligned to the diagonal line, that means you find the exactly correct answer. And then there are a few internal model parameters, and you can see that my method can find it very close to the diagonal line. And this is the artificial agent data. So I first of all build an artificial agent and try to find their internal model based on the optimal ensemble. And that's why I know the ground truth. So I know what the true internal model is. But in case of the monkey, we never know the true model. So what we can say is, our finding internal model parameter can explain this monkey's behavior. So we got this graph after I come back to Korea. So our new lab member who took over my project finally get that wonderful graph. So you can see that the agent and the monkey's trajectory is the blue. So monkey never repeat the exactly same action, but it has some pattern, right? And then we find that our agent finally find the internal model, and if we use that internal model, we can explain the monkey's action. So that was so exciting. Okay, so far what I did, so we tried to answer can we model the minds of the others and try to explore inverse rational control approach. In here, our goal was to try to infer the internal model of the agent using observable data. And the method is train the ensemble of optimal agent and then find the parameter theta that explains the observable data the best. Okay, so that's the second part. And third part, probably most of people in this room is asking me, okay, that's so much fun, but where can we use it? So after coming back to Korea, what I do in my lab is the first project is a mixed autonomous traffic. So what I'm interested in is a human AI interaction. I personally believe that the first scene I can see the human AI interaction will be the autonomous driving technique. So what makes the autonomous traffic means is a combination of the autonomous vehicles and human driving vehicles is presented on the road at the same time. We are already seeing that one. But challenges in here is human drivers often make unexpected behavior. We are the problem. So every human driver has his or her own driving pattern. So from the perspective of AI, from the perspective of autonomous vehicle, human drivers are the most difficult agent to interact with. I personally so believe that one. So what I want to do is, can we infer the overall characteristic of the human drivers by observing their behavior? So this is the work from Dongsu Lee in my lab. What he tried to do in here is we make a simple example. So like we just simplify the 3 different kind of characteristics. The first one is target speed oriented. So how much do you care to keep the target speed? And the second one is safety distance oriented. So how much do you care the safety distance with the neighbor vehicle? And the third one is lane changing frequency. So somebody love to changing the lane. Somebody gets scared to change the lane. So that's like somebody's driving pattern. So what I did in here, we made a true point, and then we just randomly start the initial point, and wherever initial point is, we always find the true point based on the inverse rational contour that I explained before. That was pretty exciting, yeah. So what we want to do from this work is, first of all, we understand the others' pattern, and then we can predict that their behavior in the future once you understand the person, and then you can interact with them with a better decision. Yeah, that's what we are doing here. It's a very small baby step, but exciting steps. And the second topic that I'm working on is cooperative network formation of a mobile robot. So the challenges in here, you imagine that you're in a disaster scenario or a military scenario, so there is no network infrastructure is available. By the way, I'm coming back to communication system. Finally get there. So yeah. So there's no networking infrastructure is available in here, and no centralized control for building, managing network, and it's impossible to get to that area as a human being. So we need AI or we need some machine to get there and then do some work. And mission in here is simply deploy the mobile robot and let them make the network. Let them build an add-on network for us and then send the source data to us. Take a video camera to the disaster area or like military area that took the photo and they give me in a destination. So what it is my outstanding student, Nayang Kim, is working on it. So we try to make the ad hoc teamwork. So what ad hoc team means, like teammates must work together to achieve a common goal, but without any prior agreement regarding how to work together. So those are really never agree that I'm going to take the source part, I'm going to take the destination part, I'm going to take the in the middle as a relay node. Nobody agreed in a before movement, but they do make a role based on their learning. So what I was really curious is how to determine the role in this scenario. And what we found is, first of all, it successfully find a location and build a network. That was so exciting. So here is a source node and here is a destination node. And then we give them a 4 relay node. So that can be a drone, that can be a mobile robot. And we really wanted them to make a nice add-on network to transfer the source data to the destination. All those 4 agent comes from the destination. So initial point of their location is a destination. And then as they learn the policy, they make a wonderful add-on network. That was the first thing I was so excited to see. And the second thing is, then I was really curious, how do they make a role? Like we never let them exchange any message. What they just receive is a reward function that can be a throughput from the destination. So destination assume that like broadcast the reward. That's the only information that they can receive. And what we find it, or we are still actually looking at this, is how they determine their role is based on their early experience of exploration. I think that makes sense. So like as a young people, like when they are young, all the reward they get kind of determine their personality characteristic, right? So I think like the agent as well, AIs as well, gather their role based on their first very significant reward. So based on that experience, the agent get a role. So this is still ongoing work. So yeah, that's all. So the conclusion. So I drew 3 questions in this tutorial. I know like those 3 tutorials are so different, but I hopefully make sure that combine everything together, even though it looks really different. So first one is how do we make decision? So I introduced the deep reinforcement learning approach. So we build a policy to determine the action based on our belief. And this process can be explained by the deep reinforcement learning. And the second question was the fun part. I show you the monkey video. Can we model the mind of others? So an agent builds a policy based on his or her internal model. And inverse rational control can find the internal model parameter that explains the agent behavior the best. And the third one, come back to our engineering and communication system. The first one was I introduced the mixed autonomy traffic scenario. So inverse rational control can find the driving characteristic of a human driver and predict their behavior. And the second one was a cooperative network formation of a mobile robot. So mobile node or mobile drone or whatever it moves can build an ad hoc network by cooperating each other. So yeah, that's all. We are hiring for the postdocs. So if there is anyone who wants to work with me, and please email me. And if you need more information, please come and visit my webpage. Thank you.
네, 고맙습니다. 예. 예, 뭐, 프리리퀴짓부터 굉장히 친절하게 설명을 잘 해주셔가지고요. 예, 사실 이렇게 비기너들 아마 강학습이나 멀티 에이전트 시스템 비기너들도 아마 학생분들 중에 있을 텐데 아마 다 충분히 다 이해하셨을 거라고 생각이 듭니다.